People often say black holes erase information. They're wrong in a crucial way. When two black holes spiral together and merge, the event horizon of the remnant swallows more area than the two originals could account for. The entropy, which counts the number of microscopic ways a hole could be arranged, rises. In other words, information isn't simply lost. It is redistributed, stored in the surface itself and in the ripples of spacetime that escape. But how can something as simple as a surface hold a memory of every particle that fell in? What does a gravitational wave carry, and what doesn't it carry? The mystery sits at the boundary between thermodynamics and quantum information, in a place where geometry speaks in equations and truth hides in subtle correlations. This is the story of horizon entropy, the idea that information survives mergers, encoded in a ledger written on the horizon and whispered through gravity. To understand why this matters, we have to travel back to the pre-merger era of black hole physics. In the early 20th century, black holes were exotic solutions to Einstein's equations, but scientists treated them as simple vessels: a mass, possibly charge, a spin, and nothing more. The no-hair theorems of the 1970s claimed that all the complicated details of what fell in were erased, replaced by a few macroscopic parameters. That vision made the information paradox seem inevitable when quantum mechanics demanded unitarity. If Hawking radiation is nearly thermal, where does the data go? Bekenstein, in the 1970s, proposed that a black hole carries an entropy proportional to its surface area, suggesting a finite, countable ledger of microstates. Hawking's discovery that black holes emit radiation seemed to threaten unitarity even more, because a thermal bath appears to carry no information about the initial matter. Yet the energy radiated by a merging pair is not wasted. It leaves the holes with larger mass and different spins, and the event horizon expands. The 1990s and 2000s brought a flurry of ideas. Some argued that the information could be encoded in subtle correlations within Hawking radiation. Others invoked holography, the idea that a volume of space can be described by degrees of freedom on its boundary. In the context of mergers, the gravitational wave signal itself becomes a fossil record of the journey from two separate spacetimes to a single, larger one. LIGO's first detections in 2015 confirmed that anti-intuitive mergers do occur in the real universe. The waves carry the fingerprints of two spiraling behemoths, then the quiet of a settled, spinning remnant. Still, the paradox remained until new ideas about horizon microstructure emerged. The horizon might not be a featureless boundary after all. It could be threaded with a kind of quantum hair, soft excitations tied to gauge symmetries, that stores information about everything that fell in and, in principle, can influence what escapes as radiation and memory. That rise in area means more microstates could realize the same macroscopic whole, so the information about what fell in is not simply erased. It is redistributed into the final geometry and the quantum fields tied to it. To make this tangible, imagine a library of memory. Each microstate is a possible catalog entry that could describe the whole's interior. When two libraries fuse, you don't delete pages. You merge catalogs into a bigger library with exponentially more entries. The information remains, but accessing it directly requires looking at correlations rather than individual pages. In semaphore gravity, those correlations are faint, yet they exist. The key modern twist is the idea of soft hair. Low energy, long wavelength excitations on the horizon linked to gauge symmetries. They don't show up as a sharp line in a spectrum, but they can encode how the horizon rearranges itself as matter falls in and energy rushes out as gravitational waves. The memory effect, a permanent displacement left by passing waves, offers another concrete record. In merging black holes, soft hair and memory work together to keep a trace of the past in the final state, and in how the radiation and the space-time geometry finish their dance. So the merger is not a wipe, but a rewriting. A larger ledger, richer in information, accessible only through the right questions about correlations, memory, and horizon structure. Why does this matter beyond black holes? because horizon entropy is a bridge between geometry and information. If information survives mergers and perhaps entire collapses via soft hair and holographic descriptions, then unitarity remains intact in gravity. This reshapes our view of spacetime as an information-theoretic object. It supports the holographic principle. The content of a region is encoded on its boundary. It hints at a deeper quantum gravity. The microstructure of the horizon is the key to describing quantum states of spacetime. In practical terms, it reframes how we think about afterglow signals. Gravitational waves do more than carry energy. They carry correlations that connect the distant past to the present. Gravitational memory could be a fossil record of information crossing the horizon. The possibility of soft hair, though subtle, offers a concrete mechanism by which the universe preserves what would otherwise be lost to the void. From a thermodynamic ledger to a quantum memory, horizon entropy shows that information survives not by magic, but by being woven into the fabric of a horizon and the gravity that surrounds it. The merger is a cosmic reminder. Massive objects collide not to erase the past, but to rewrite it with more states. In the quiet after the storm, in the subtle memory left in detectors, and in the soft gravitational whispers at the horizon, the old information persists. The mystery endures, but the path to understanding grows clearer. Information and geometry are two faces of the same coin, bound by entropy and encoded in horizon structure. If we learn to read the right correlations, we glimpse how quantum gravity stitches together information, space-time, and reality itself. If you want more, subscribe.